Thank you very much, Eric. Oops, it's that wasn't me who was controlling that, but okay, here is the title anyway. Yes, thank you, Eric, and thanks to Raul and all the organizers of this very nice workshop. And thanks for allowing me to present this work. This work was done in collaboration with Xin Wang, Peter Plechach, and Anders Sepesi. All of us are at KTH in Stockholm, except for Peter, who is at the University of Delaware. So here are two models to describe matter: quantum mechanics and molecular dynamics. The quantum mechanics, here we have the so-called Schrodinger equation, which is an eigenvalue problem. So the eigenvalue would be the energy, therefore it's called E here, it's denoted E, and the state is the so-called wave function, denoted by psi, that describes the state of a system with this energy E. So that would be one way to characterize a molecular system. The other one is doing molecular dynamics, which we have here, which is in this case if we think about constant energy, then it's Newton's second law. So we have the mass of the particles is called mj. Later on, we will have the particle, parameter m. We assume that the mass is the same for all particles, or all nuclei in the system, or it is rescaled in such a way that we have just one mass particle, a mass parameter. Okay, and p is the momentum, and we have what is often modeled a sum of pair potential. So each particle feels all other particles in a pairwise interaction. So then one could ask, what should one do? Should one use one or the other? So there are reasons for choosing both of these methods. So to start with, if we think about this, the Schrodinger equation in quantum mechanics, it's a nice, well-defined object. Here I wrote out this operator h hat. It is a partial differential operator. So here, the mk, this is the mass of the heavy particles, the nuclei in the system, if we have a scaling such that the electron particles have mass 1. So the capital M is the quotient between heavy and light particles. Okay, so these first terms, this term refers or corresponds to kinetic energy of nuclei. This is the kinetic energy of electrons. And then we have Coulomb interactions. So we have Coulomb potential acting between nuclei and electrons, and we have the electron-electron interaction and the nuclei interaction. But, or I should say, and as you see, this could quickly become very high dimensional, this problem. So for instance, as I wrote here, if we have a water molecule, fairly simple object, well, this operator is then acting on a space of dimension 39. So very high dimensional PD problem to solve this eigenvalue problem. So that is definitely a big drawback with the Schrodinger equation, the computational complexity. I mean, it's just too computationally costly to use that directly for simulations in high dimension. But there are also very nice aspects of Schrodinger equation. One being that there are no sort of unknown parameters there. we have this Planck constant. Now we have units such that I didn't put it there, but it's a Planck constant, and we have these interactions, Coulomb interactions. Everything is completely known, and it's just a linear partial differential operator. So sort of nice theory. Everything is nice, except that it's very difficult to compute it. On the other hand, for molecular dynamics, yeah, that is possible to solve for much larger systems. But there is also the drawback that the model is much more uncertain. This potential that one used to move these particles around needs to be determined somehow. I mean, it's not given to us a priori. And then what one could do in different ways. I mean, one way would be to do the more top-down approach. I mean, we have a model that we try to adjust to observations. I mean, experiments. Or one could do what we will talk about here. We do the bottom-up approach. So we will use the quantum mechanics as the fact, and then we try to find a molecular dynamics that mimics the truth, so to speak, the quantum mechanics well. So we'll try to address this question as well. How accurate is this approximation then? We want to accurate in the sense of approximating the quantum mechanics. One such approximation is what is called Born-Oppenheimer approximation. So this is using the idea that the nuclei, they are much more heavy than the electrons. So the idea is the nuclei, they move sort of classically. We have a classical dynamics for those, and the dynamics for the nuclei is determined by the electrons. The electrons are treated quantum. So we single out the electron part of this Hamiltonian and compute the lowest eigenvalue. So this eigenvalue depends on the nuclei positions only parametrically, and so we have some kind of energy landscape for the heavy particles to move on. And we will return a little bit to this Born-Oppenheimer later on. This is not the main topic here, but maybe you have heard about that. So that is one sort of connection, direct connection between Schrodinger equation and molecular dynamics. Okay, so let me note here that just for theoretical purposes, for simplicity, we will assume that the electron part of the Hamiltonian, we approximate this by a matrix. So it's just for simplicity of theory. So I mean, say for instance, we do a finite element discretization of electron space or something. I mean, we have the operator and we discretize it somehow, but this discretization could be very fine. But anyway, it's given like a matrix. So that means this eigenvalue problem, the Schrodinger equation, then has a wave function that will be a vector. And also it depends, I mean, it has a dependence on space as well, space of the heavy particles. So we had the word canonical ensemble in the title of the talk. So this is here. We want to estimate things like what we have here. A hat is a quantum observable, and we would like to compute such an average. So why would one do this? Let's see if this fancy it worked.
The bond should be on the side. I think to the right side.
What did you say? There was this IT guy who showed me this just recently, but anyway, this is safer. I hope you can see this. I will not write so much, but anyway, this canonical ensemble, it corresponds to the following situation, that we have a system. We have a system here, say, n particles. Maybe you can. Okay, great. What's the bottom on the bottom? Okay, thank you very much. So we'll have this situation that the system under consideration, our n particles, is sitting in a heat bath. So it's not an isolated system. So that means it will not conserve the energy, this system. If you have an isolated system, then you have the Schrodinger equation. I mean, there is an energy eigenvalue, and I mean, it conserves that energy. But if you have this situation, there is going to be a certain probability of the system in question taking on the different energies, and this probability is Gibbs distributed. So this is going to be proportional to e to the minus t divided is energy En, possible energy level of the system divided by T. Sometimes we put them Boltzmann's constants, kBT. So if we have units such that this is one, it looks like this. Oops. So this we will also write as e to the minus beta En. So the inverse temperature is called beta. So we have that these probabilities. These are what we see here. E to the minus energy divided by T, and then we have the observables. So these phi n are the eigenfunctions of the Hamiltonian. Okay, so let me then tell you what is this quantum observable A hat. So here is a bit nasty expression as it looks from the beginning. This is called Veil quantization, which is giving us the relationship between quantum observables. So here is this operator A hat, and the classical counterpart is the so-called symbol, which is a function of the state space x, the position x, and the momentum p. So how does this work? So let's consider, for instance, the Hamiltonian, the energy. So here is the classical Hamiltonian, kinetic energy and a potential that depends on space x, and in coordinates such that, yeah, it just looks like this. So sort of the corresponding dynamics has speed of order 1. Okay, so let's say that we consider the potential part here. So V is just a function of x, that this A would just be a function of x. Okay, so then we see it's ax plus y, and in this inner integral is an integral over p. So that means this goes outside of that integral. So the integral over p is just this integral of e to the up times p. So this is then a Fourier transform of constant 1. So this is becoming a delta x minus y. So then we see we put x equal to y, so we get a of x and phi of x. Or if a is equal to v, it's just I mean, we see this operator is just the multiplication operator for v of x. And if we would take, for instance, the kinetic energy, p squared, so this means we have the transform of p squared. Well, this corresponds to two derivatives of the direct delta. So again, this gives us this Laplacian. So in a way, the Weyl quantization gives us sort of the right thing for variables of x, and it gives us the right thing for variables of p, and then sort of interpolates for all other observables as well. Okay, so if I go back here, we wanted to compute something like this. We have this sum and this inner product, and then we have the exponential. So if we disregard the exponential for the time being, we have this kind of sum. So what do you say? Do you recognize this expression? Would one give this a name? You can just shout it out if you see or think what. So here these phi n's, these are all eigenfunctions. They in fact will form a complete basis of this function space. So this is the trace of this operator. And I denoted up here, or I just noted up here that this operator is, I mean, if we do this integral over p, we are left with something which is a function of x and y. So a hat is given as a with an L2 kernel. So a hat of phi of x. This can be described as an integral of this kernel xy phi y dy. And then the trace of such an operator. This is the integral of, put in xx, like that, kxx. So similar as if we would have a, if it's a matrix, then the trace can be computed as just summing the diagonal elements. Okay, so that is what we do. We have this operator here. Okay, we put x equal to y. Still, we have this integral over p, and then you see x is equal to y, so we get this integral over x and p. So this looks kind of innocent, but if you think about it, this is a huge simplification here. What's on the left-hand side? This is if we have a Schrodinger equation, you say dimension 100, we have to compute all eigenfunctions, and then compute all these inner products. That's sort of out of reach. Whereas on the right-hand side, it's just an integral here over state space. Okay, dimension 100 or 200 or whatever. But this is sort of this is possible to compute. So this is the so-called Weyl law that is really nice. And the same also holds if we take two operators, a hat, b hat. Okay, we have the same, exactly the same as before. It's just that we have a times b on the right-hand side. And unfortunately, it does not work with 3 or more, which we would like to have. But returning to this Gibbs density, in order to obtain what we want, we see if we would have these two operators, we would choose one of them as this exponential. Then we would almost, when we take b times phi, we get almost this e to the energy times phi. There is an approximation here because, in fact, what we get is sort of the order of exponentiation and quantization in the wrong order. So it's not exactly right, and this is sort of a part of the approximation result that we will see. Okay, so we wanted to also do this for time correlations. So here is a motivation. Why would one consider such operators? So for instance, if we would like to compute diffusion constant, then we would need to compute this correlation of paths at some time apart. So then we would have such a time correlation that would be needed to compute. Okay, so here is an older result. This is with us and also Akko Kammonen, who's here, as you know. Okay, so I will not describe this in detail, but I will just say that what we have here is we have such a time correlation, and there is, I mean, it's a symmetrized version here. So it's sort of these two terms on the left-hand side. That is not so important. So this A hat has some time dependence and so on. And on the right-hand side, we have a corresponding molecular dynamics, or I mean, integral over state space. So computable, for instance, using molecular dynamics. So here we have a certain measure we have to integrate against. So for instance, one could do some kind of Langevin dynamics to get this, to integrate this measure. And the observable here, we have done some kind of diagonalization of the operators. But in fact, this time dependence, so corresponding to the A hat tau here, in fact, what we need to do is we need to solve the time evolution of this Hamiltonian system using not only, as in the Born-Oppenheimer system, not only the ground state, but sort of all excited states as well. So that was a drawback here for this. So we thought, so it is a result, but it's not perfect in that sense that to actually compute this evolution here would be very costly. And also it uses the diagonalization of the operators. So let me not sort of go into this too much. One can just note that in general, if one have a potential V that is depending on space, there will sort of generically be positions where the eigenvalue surfaces cross. So for instance, if one compute the eigenvalues of just such a 2x2 symmetric matrix, it will look like this. So the eigenvalues will coincide if A is equal to C and if B is equal to 0. So there are two conditions. And yeah, so if we are in dimension 2, these eigenvalue surfaces would look like this. This is what is called a canonical intersection. So the eigenvalue surfaces would look like that. And so in general, these intersections take place on manifolds of codimension 2. So these positions are sort of 2 dimensions less than the full dimension. But anyway, and if they coincide, these surfaces are also non-smooth, as these cones are look like they do. Okay, so So far, I never said what is this time evolution of the operator A hat T. So this is we can understand this by using the time-dependent Schrodinger equation, which you might have seen. It's the equation here on top. So this is the Schrodinger view of the world, that this wave function evolves in time following this kind of equation. So then we could write the solution to this equation using this exponential function. And in this other view of the world, Heisenberg view, the operator is what is changing in time. So this is the definition then of this A hat T. So it's the same operators as we have up here. So the expectation sort of would be the same anyway. But that is a motivation. Why does the operator look like this? But okay, so that is how this time dependent observable looks. And so what we would like to do is the following. We would like to approximate this quantum mechanical observable using also this Gibbs density by a molecular dynamics counterpart. But now what we will see is that instead of, as before, we have an evolution on every energy surface. It is going to be sufficient in some sense. I mean, there is an error in this as well, but there is just one evolution here for sort of corresponding to this A hat T. So we have a Hamiltonian system, and this Hamiltonian is called lowercase h. So the question is, what should that function be in order to have something reasonable? And what would be the error? I mean, if we compare these two entities, the quantum mechanical and molecular dynamics. So this is then the answer here, this theorem, that this mean field Hamiltonian is defined like this thing here. And if a number of conditions is satisfied, for instance, the observables are not to depend on the electron coordinates. So therefore, in this picture, when we have discretized the electron space, it means that we have assumed that these observables A and B are just scalar. Okay, so then this result holds. Oops, yeah. We can approximate this quantum mechanics observable by molecular dynamics with an error. Again, we have this term inverse M, and I remind you what it is. The M is the quotient between heavy particles, the nuclei, and electrons, and it also depends on this time involved in the time correlation. Okay, so let me show you a few very simple simulations. So they are simple primarily because we want to compare with the quantum mechanics. So as I said, this is very costly to perform for large systems. So here we have sort of the smallest possible. It's just in one dimension, and this potential V that corresponds to the electron states, we do the smallest possible. It's just a 2x2 matrix. So here is a picture of these eigenvalues. So the yellow is the excited state, that is the larger of the two eigenvalues, and the purple one, which you see here in the inset, is the lower one. And the mean field corresponding to the dynamics in the theorem is somewhere in between here. Okay, so using I mean, if we start with this quantum mechanics observable, we can, if we choose these variables to begin with, as we don't have any time dynamics. So A is just identities A. We choose a simple A, and B is an observable that only depends on X. Then this thing, that we have in the numerator here, we can write this as this thing here. So you see, this is an integral over this operator B of X, and we have this density, the sum of phi n squared times e to the minus beta times eigenvalues of the operator. So here, I mean, this is sort of done numerically here. For this very simple problem, we can compute the eigenfunctions and eigenvalues numerically. So, but with a high order method, so we believe this is an accurate density that we obtain. And similarly, we can do for the molecular dynamics. We can compute corresponding density for that. Okay, and then we get this here, a plot of these densities. So the blue is the quantum mechanics density. Yellow dashed line is what we get from the mean field, and in this picture they coincide almost perfectly. And if we would do instead the Born-Oppenheimer, that is using only the ground state, well, that corresponding density would be this purple one. So clearly that one is slightly off here, whereas the mean field is looking good. And here is a picture where we just take the pointwise difference between the truth, the quantum density, and this mean field. And this mass parameter is changed here to show the impact of m. So when m is 1000, we sort of see no difference at all in this picture. So that looks as it should. In this next picture, we have a plot showing the L1 distance between the quantum truth and the approximation. And again, here it really converges as inverse of m. So that was a test for the stationary case. Let me show you as well a test here for a time correlation. So we have an observable. So we had this observable a tau b0. So here we take the momentum at time tau and momentum at time 0. And here is a case we can choose some parameters and this temperature parameter, such that in this case the mean field potential is almost coinciding with the ground state. So what we have in the lower left panel here, we have in blue the quantum mechanics, observable, as it depends on this tau. And then we have the three possible molecular dynamics simulations. The red and the three molecular dynamics, they completely coincide here. We do this mean field, or we have the ground state, that is von Oppenheimer, just using the ground state, or ES stands for excited state. So this is the first result where we use the dynamics on all energy levels. So the more sort of costly method. Okay, and this, yeah, they all behave pretty much the same. For this case, since yeah, the mean field energy is coinciding almost with the ground state. So if we change the parameters a little bit, we increase the temperature. Here we have a case then where this mean field energy eigenvalue function is in between the ground state and excited state. So here then so the red one is what we get with the mean field, and the purple corresponds to Born Oppenheimer. So here we get slightly better. Although, oops, I was that again. Let's see if I can. Okay, so but it's not such a big difference anyway as what I would have thought, and this is the case when we have tried different things. But of course, in order to be able to compare with a quantum mechanics observable, then it's possible only to do very small systems. But anyway, not such a big difference in these experiments as compared to just doing the ground state dynamics. Okay, so let me talk about one aspect that was a little bit swept under the carpet, and that is, I mean, how would one compute this mean field potential H? So if we have a low temperature, then it's close to the ground state of the system. And if we have higher temperatures, it takes in excited states as well. So in some sense, one would think, okay, but this should be the simplest then if we have a low temperature. But then again, we would need actually to compute the ground state for the electron part of the Schrodinger equation. And again, that is a PD in high dimensions, so it is very costly. And there are numerical methods, density functional theory, or so-called Hartree-Fock approximation of this eigenvalue. But still, it's of course this is the big cost in this problem. So let me discuss another possibility here to do more probabilistic things. So I remind you that we want to compute this. I cannot mark this now. This is the expression we want to compute, this mean field Hamiltonian. And just an observation here is that it suffices to compute this so-called partition function Z. If we have this, that is the denominator here, we can just differentiate the log of Z with respect to beta, and then we get our H. So the question is, how can we get this partition function? So let's think. Okay, so now I sort of switch back. I said that we have the electron Schrodinger operator. We discretize that, so we have a matrix. Now I go back again and let the Schrodinger electron operator be in its original continuous form. So it has Laplacian with respect to the electron coordinates and this potential, the potential which is then the Coulomb interactions between with all particles. Okay, so with that Hamiltonian, we could consider the following parabolic PD. Okay, we have this terminal value problem. We have the parabolic PD and the terminal value problem. Okay, the solution to this problem is given as this solution operator times the terminal state G. Okay, so then we see if we set time equals 0, we have this e to the minus beta h that we're interested in. And also we have the Feynman-Katz formulation. I mean, a way to represent the solution to this parabolic PD is as this expectation. Right? So that would give us a way sort of to maybe get our hands on this object that we want. So U is this expectation I have here, where X is a Wiener process shifted, so it starts in a position X. Yeah, I call the time going from T to beta for R here. So anyway, I think you have seen this. Okay, so this expectation we have here, if we that's an integral over state space. So if we write this as an integral over all paths that start in X and end up in Y with the corresponding probability measure of all such paths, we get this representation here. So we see again, U is given as an L2 kernel times this function G. And again, if we want to find the trace of the solution operator, that means integrating kxx, as I wrote over there. Okay, so this is what it boils down to then. This trace is in some sense computable like this. We have this Wiener process, shifted Wiener process. We integrate over all starting positions X. And for each starting position, we need to compute the expected value of this exponential, e to the integral of potential along this path, x r, over such Brownian bridges. So here, this is the simple case. So here we did it for so-called distinguishable particles. So the trace is just the trace over the entire space. If we have fermions, such as electrons or bosons, it becomes more difficult, because then we would take the trace over a subspace. For bosons, it's the space of all symmetric functions, and for fermions, the space of all anti-symmetric functions. So in fact, then the corresponding expression is similar, but then we would have this signature of a permutation that comes into play, especially then, or for fermions, then this exponent is 1, so the signature could be -1 or +1. So this means if we say we have x, the starting position is x1, x2, x3, as a permutation could be, for instance, x2, x1, x3. So depending on the signature of this permutation, we get the whole thing with a weight minus or +1. And that is called the fermion sign problem. That is, I mean, it is the whole thing that we're interested in. But each of these integrals, might be much larger than the end result. So say that the difference is maybe of order 1, but but each of the integrals is of order 1 million, say. So if you would do like a Monte Carlo simulation, you have to have super big accuracy because you have huge cancellation there. So in some sense, yeah, so this is sort of what we are thinking about, but this difficult problem, but maybe one could sort of get a hold of this mean field potential in that sense, using such ideas with these path integrals. Okay, so I will not say so much about the proof. I can just say that we want to compute this quantum mechanical observable using the molecular dynamics, and we have the expression for this time-dependent observable corresponding to this this sort of what's it called, Heisenberg relation. So we have this evolution equation for A hat, and for the classical one we could form a similar evolution equation that involves a so-called Poisson bracket. So then one could show that these right-hand sides, they differ of a certain order. I mean, the difference is of order m inverse. So that is sort of moving from the quantum dynamics to classical dynamics. Okay, and then one can use Duhamel's principle. So we want to see the difference between these the classical dynamics and the so when I write the lowercase a here, it's the classical dynamics and then quantization afterwards. So sort of, yeah, they are not the same, the capital A and lowercase a. Anyway, so there is a way to bound the size of that quantity, which gives us one step of the proof, and yeah, the second one. Yeah, I think I skipped these details because if you are interested, you can look into it. But I just skipped to few references here. I have a reference which I haven't talked about, but if you would do not this case of canonical ensemble, but constant energy, and do the correspondence between quantum and molecular dynamics, there is an older result here, which and in that case it's actually much more complicated. And then I listed these two papers here corresponding to canonical ensembles. So that is it.
Thank you, Mattias. Do we have any questions on this talk? Neil?
Thanks for the talk. I just had a quick question. So before I ask it, from my understanding, the bound that you provided with the m-1, so you can attain the canonical rate, but you lose some form of accuracy with the mean field approximation. And this, what you've drawn right here, this conic intersections. So this comes naturally with the mean field approximation, where you don't lose this form of accuracy in your numerical experiments. I got a bit confused because it seems to me that this is quite crucial for you for the mean field approximation for your numerical simulations, but I wasn't so sure. So it's more of a query than a question.
Yes. So in in this mean field approximation, we never need to do this kind of diagonalization of the parameters. So therefore that is not so important here. This sort of smoothness of the eigenvalue surfaces as before, when we actually did the diagonalization and sort of was using all the eigenvalues. It is this other expression that is here in the mean field, that trace of h hat times e to the minus beta h.
Mhm. Okay, thanks.
Okay, do we have any further questions? If not, let's thank Mattias once again for this nice talk. Okay, so this ends today's session. And let me just remind you that there is one more session of this workshop tomorrow, very late. It starts like 5 in the evening or something. So the rest of the day is for collaborative work, or for some of you, the excursion. Thank you all so much.